For chapter or section 11.11, which is applications of Taylor polynomials, so we will really not look at the actual applications to science, like, well, the textbook includes applications to physics, in this case to optics, but there's a lot of applications in which you can use these Taylor polynomials or Maclaurin polynomials. Actually, in physical chemistry, those of you who are chemistry majors or some engineering majors, which we will take thermodynamics course, well, in some situations you will work with PVT system, for gases or for other situations, pressure, volume, and temperature. And in some situations, you will expand a temperature function, a pressure function, or a volume function in terms of a Taylor polynomial. Well, when you will get to see those when you get to those courses, those of you who are going to take those courses. In the meantime, well, the only thing we're going to do about this section is look at the remainder theorem and Taylor's inequality. What is that for? Well, so number one, all we have been doing for the last couple of sections, which is approximating functions using either Taylor polynomials or Maclaurin polynomials, depending on the center of the polynomial, is ultimately to come up with an approximation. But recall that an approximation, it's just that, an approximation, not the actual value. And of course, there will always be some difference between the actual value and the approximated value. However, in this section, what we're going to do is use Taylor's inequality to find out what is that maximum error of using a given expansion, say the quadratic expansion, for example, the cubic, the more terms that we add, recall that's going to diminish the error a lot. All right. Let me give you an example with numbers. So for example, 1/3. What is 1/3 approximately equal to? 0.33, right? Well, in this case, we don't use the equal sign. We just use the approximation because, well, it's not one number that we can divide evenly. Like one half is exactly 0.5, or 1/2 it's exactly, 1/4 it's 0.25 exactly, or other fractions that have exact decimal versions. This one doesn't have an exact decimal version. That's only an approximation. Now, if we want to express this result as using an equal sign and not the approximation symbol, well, you might want to do the following. Number one, 1/3 equals, yes, 0.33. And in this case, well, plus some remainder. And there's a little typo here. I'm missing an A here. Remainder is something else, right? So, of course, that 0.33 plus remainder, that remainder is the number of decimal places that we are not taking into account when we say 0.33. We're leaving out that infinite number of decimal places, and well, in order to for practical purposes, just use 2 decimal places, 4 decimal places, and in some cases the approximation has to do with the situation you are working with, that it's dictated in a way by the number of significant figures, that thing you use in chemistry, in physics, Of course, we can name a better approximation of this number. How about 1/3 equals, not approximately, 0.333. You can add a bunch of 3's, It's a better approximation, isn't it? Because we're using more decimal places. But ultimately, that's what it is. It's just an approximation. And yes, this value is still going to be off from the actual value of 1/3. And for this reason, to call it an equal sign, we have to add that remainder, to take into account that remainder. All right. Well, I'm not going to do another one, but I think you see the picture here. All right. Well, so the same happens with polynomial approximations, and I think you are already familiar with this idea when we were working on the second degree approximation, the cubic approximation, how adding more terms to more degree terms to our approximation improves the approximation of the value and making the gap between the actual value and the approximated value a smaller value, pretty much, if you will, overlapping the two values. For example, you might remember the picture with the expansion for the exponential function. Well, let me actually get into the theorem first, and then we discuss that part. Yes?
Is your battery connected?
No, it's not, but I have it here. Thank you.
I got you.
Thank you. So, in this case, the same situation occurs with polynomials, and in the same way that with numbers. So we got the approximation plus a remainder. Approximation plus remainder. The two quantities added together will give us the actual value. So, as an example, e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial. That's simply the cubic approximation, which is a decent approximation, you know. And in this case, well, notice in this case I'm not using the approximate symbol, right? I'm not using that symbol. I'm actually using the equal symbol because in this case we're taking into account the p sub 3, which represents the Maclaurin expansion of degree 3. But if I want to make this equal instead of approximately, we have to add the remainder Rn, in this case the remainder of using the third degree polynomial. Alright? So, well, actually let me call this, let me use word, remainder. And this is represented by all the terms from degree 4, 5, all the way to infinity. Infinitely many terms in this case. So that's R sub 3 of x. To come up with a better approximation, of course, e to the x equals, for example, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus x to the 5th over 5 factorial plus x to the 6 over 6 factorial. Well, in this case I'm using the 6th degree polynomial, Taylor polynomial, which in comparison with the cubic one, that's going to give us a better approximation. And you might recall the graph in the last section, or the last couple of sections, I forgot which one he said. We did the comparison of the exponential function with four different graphs. Number one, along with the linear approximation, which really overlaps at one point because that's the equation of the tangent line. And then we did I showed you the quadratic approximation along with the function, which in this case overlapped at a larger number of values, not just tangent. It was overlapping at more points, and then the cubic was overlapping at more points. And by the time we got to the 4th degree approximation, we got that exponential function and its approximation overlapping at even more points. So we could have used that quartic polynomial to approximate values of the exponential at a wider range. So now imagine what we can do with the 6th degree approximation. It's just going to be a lot better. But still, again, it's what it is. It's an approximation. And that approximation has to include its remainder. But in this case, well, this will be the remainder of using the 6th degree, and this is the piece of 6, which is the Maclaurin polynomial of 6 degrees. Alright? So that's the idea. Now, well, the picture here is, let me see if I have room for the picture. I'm not gonna have room for this. Well, I'm gonna do that actually on the actual example. So number one, here's the theorem, and don't be scared about all these symbols and inequalities and factors and factorials here and there, you know. I know it's kind of weird. This inequality is kind of weird. However, before looking at this inequality, let me go back and review the basics of inequalities, or rather, how do we interpret inequalities? For instance, we have the inequality x greater than or equal to, or no, let me do the less than or equal to 3, and the inequality x greater than or equal to 3. So what comes to our minds when we read the first statement, x less than or equal to 3? Any ideas on what does that represent? One. X has to be less than 3, right? You know, all the values of x that are less than 3, you know, that is all the values that are less than or equal to 3. All right, I mean that's what you know since I guess basic algebra, right? When you first learn about inequalities, how to represent, what does the less than represent versus the less than or equal, you know, all the implications here. And on the other hand, this represents all the values that are greater than or equal 3. Well, that's the algebra definition, you know. That's either the intermediate algebra or advanced algebra, college algebra, or pre-calculus definition. That's what it means. That's the language behind this kind of statements and words, all right? However, another interpretation of this inequalities, well, how about we graph them? There's a 0, 1, 2, 3. In this case, I'm going to go like this in a shade. So, if we observe this set, x less than or equal to 3, that set has a largest value, all right? An inequality of the form less than or equal a number, 3, 5, negative 7, your favorite number, it implies that the set has a maximum value. So this set has a maximum or a largest value at or of. And on the other hand, all right, if we shade this set, you know, this interval right here, well, is that set still containing a maximum value? What do you think about this one? It's a minimum value. It's a smallest value, all right? So in this case, this set has a minimum or a smallest value of 3. You may or may not interpret inequalities this way. So every time you read statement like this, okay, it's all real numbers, less than or equal, less than, greater than or equal, greater than, whatever. But I mean, I wonder if you ever think about these sets as, instead of just listing or interpreting what numbers are included in the sets, to actually conclude that depending on the orientation of the inequality sign, we may have a maximum value or we may have a minimum value. And well, for Taylor's inequality, if you look at the madness that you have in the definition box, we have an inequality of this form. X less than or equal some number. In particular, well, this one is going to be the absolute value of some quantity. I know it's a lot of symbols, parentheses, subscripts, factorials, powers, absolute values, but ultimately this inequality here is an inequality of the form x less than or equal to a, in which we are going to obtain a maximum. And that's because what we're going to do in this section is find the largest possible error of using, say, the quadratic approximation, the cubic approximation, the quintic approximation, well, depending on the case. And again, regardless of the approximation that you use, there will always be a difference between the actual value and the approximated value. But in Taylor's inequality here will tell us what's the largest difference in between the two of them. So let's go ahead and do one example for this. And I know, yes, we'll see this inequality, we'll work it out in action. Don't worry about memorizing it for now and trying to understand it for now. So, approximate the function, and by the way, there's a little typo here. This one is supposed to be f of x equals the cube root of x, not the square root of x, okay? It's a different function here. Alright, so let's do the usual, evaluate the function at the center value, which is a, take the derivative, take the second derivative, well, actually up to the second derivative because we want the second degree polynomial. However, we will take one more derivative because that's what Taylor's inequality calls for. One, the next term in the approximation. Well, you'll see how that's going to work. Alright, so f of x equals the cube root of x, which is the same as saying x to the 1/3. Evaluate this at 8. That's the cube root of 8, which is 2. Alright, let's get the first derivative. So that's why I wrote x to the 1/3, so we can easily take the derivative. We cannot take the derivative while the function is in its radical form. So f of x, or rather f prime of x, that's going to be 1/3 x to the 1/3 minus 1, which is negative 2/3. And in this case, we'd better rewrite this, maybe not in general form, I mean in radical form, but at least in the form of positive exponent. Alright? And now, we may now evaluate this first derivative at 8 equals to 1/3 times 8 to the 2/3. Well, that's basically the same as taking the cube root of 8, which is 2, then square it, which is 4, times 3. That's going to give us a 12 in the denominator, and everything under 1. So that's 1/12. Let's get the second derivative. And careful with the second derivative, because that's negative 2/3 times the coefficient, which is positive. That's going to be negative 2/9 x to the negative 2/3 minus 1, which is basically 3/3. Isn't that going to be negative 5/3? And let's write this into, or rather as a positive exponent, and evaluate the second derivative at 8. That's going to be negative 2/9 times 8 to the 5/3. Alright, Number one, well, to simplify this, basically take the denominator. So the denominator of the rational exponent is really the index of the radical. That's a cube root. The root of 8, which is 2. Raise that to the 5th power. That's 32. 32 times 9. I don't know what's that. That's a big number. Whatever 2 over big number, that's going to reduce to 1 over 144. And these are going to be the three coefficients of the second degree Taylor polynomial of cube root of x centered at a equals to 8. However, I'm going to take one more derivative because we will need it for the Taylor's inequality. So careful, negative times a negative, that's positive. 2 times 5, which is 10. 9 times 3, which is 27. X to the negative 5/3 minus 1, which is negative 5/3 minus 3/3, that's a negative 8/3. And that's a 10 over 27 x to the 8 over 3. Alright. So let's see. Well, we're not going to evaluate this one because we don't need it for the term for the Taylor polynomial. So number one, let's list our T2. So T2 of x will be f of 8 plus f prime of 8 times x minus 8 to the first power over 1 factorial, but I'm not going to write the 1 factorial nor the number 1 power, plus f double prime evaluated at 8 x minus 8 to the second power over 2 factorial. In this case, I'm going to stop here. Well, and not notice in this case, I'm not using the approximation symbol because I'm using the second degree polynomial in particular. So that's not an approximation of the function just yet. All right. So t sub 2 will be then that'll be 2, which is, well, let me highlight these coefficients just so you can see where these coefficients here, that's the other coefficient there, and that coefficient here. So that's a 2 plus 1/12 x minus 8 plus negative 1 over 144 x minus 8 to the second power, the whole thing over 2 factorial. And well, let's simplify the negative 1 over 44 over 2 factorial. By the way, 2 factorial is 2, and dividing by 2 is essentially the same as multiplying by 1/2. So that's going to make the 144 be multiplied by 2. So T2, or T sub 2 rather, that's 2 plus 1/12 x minus 8 plus, or rather minus 1 over 288 x minus 8 squared. Alright. What's the picture here? What's really the picture? So what is it that we are trying to find? So let me do the graph of the cube root of x, which looks a lot like the graph of the square root of x. In this case, it has a negative tail in the negative direction, or going in the third quadrant. But I'm not going to draw that part because we're only interested in the positive tail of it. And in this case, this is what we're doing. So we just obtained an approximation centered at 8, and we want to know what's the maximum error of using this approximation in the interval 7 to 9. That is 1 unit away from the center on both sides. So if I go to the center here, okay, let me zoom it in so you can see the bigger picture here. What is this about? So we are essentially doing this. No, that's not going to be the prettiest picture. So let's call this f of x, and let's call the green graph, let's call it t sub 2. That is Taylor approximation of second degree. All right. Well, so of course, at the center, what do we see at the center? We see that the actual value is exactly the same as the approximated value. However, if we start going away from the center, do you see how there is that we start to see a difference between the approximated value and the actual value? And do you notice how this difference gets bigger and bigger every time? So we want to know what's the largest difference, that is the one at the upper end of the interval and also at the lower end of the interval. So we want to see these differences here. What is that difference? And although my picture is not perfect, I mean technically when we compute that value, it has to be the same difference on either side. It's just that my picture is not accurate. But I mean, all I want is to see the idea of this. That we're finding what is the largest difference in between in the ends of the interval. And here is where we use Taylor's inequality to find that remainder, find that maximum value. You'll see what about that maximum value. You'll see why I needed to go back to the interpretation of what an inequality is. In which situation do we want a maximum, and in which situation do we want a minimum value? All right. So number one, we have Taylor's inequality that tells us that the remainder of using n terms is always less than or equal some number m. Don't worry about it now, we will compute it in a second. Over n plus 1 factorial times the absolute value of x minus a to the, oh, that looks like a 9, let me make it look like an a. Okay, that looks like an a to the n plus 1. In other words, that number has the form of the next term. For example, in our particular case, we are dealing with r sub 2 because we're using the second degree polynomial to approximate our function. That's the remainder of using the second degree polynomial. So that remainder will be at most the next term, the following term, which in this case is just big M over 2 plus 1 factorial x minus a to the 2 plus 1, which, well, let me keep simplifying this. Big M over 3 factorial x minus a to the third power. So we need to work with that. Wait, no, it's not equal. It's less than or equal. Okay? Well, notice the form of the inequality. Isn't that the form of the inequality, whatever value x less than or equal some number? So what do we want in this case? We want to make sure that this quantity on the right hand side of the inequality is as large as possible. So that means both quantities that I'm about to highlight, this big M has to be the largest possible, and this absolute value of x minus, oh, actually, how about I put the number in this case, because in this case we have it centered at 8. Oops. So we can, just so we can start making more sense or connecting with our quantity. So, oh, that's fine. And also this quantity in green, both of them that involve some numbers, we want to make sure that these two quantities are the largest possible, so that overall the whole right hand side of the inequality is the maximum, is the largest. All right, Did you see that connection with the definition of inequality that we did before? Well, that's the main purpose here. So I'm going to do this calculation separately, and I'm going to use the corresponding color as in the highlight. So we have the quantity x minus 8, or the absolute value of x minus 8, to the third power. In this case, we are going to evaluate this quantity at both ends of the interval that we're looking at. In this case, the interval that goes between 7 and 9. So those are the endpoints I'm going to evaluate to find out which of the two values is going to give us the largest value. So that means x at x equals to 7 and at x equals to 9. That means 7 minus 8, absolute value of that to the third power, but well, in this case, the absolute value of negative 1 is 1 to the third, which equals to 1. That's going to give us a 1. If we evaluate this at 9, or 9 minus 8 to the third power, that's a 1, or the absolute value of 1 to the third power, which is 1 to the third power, which equals 1. Well, in this case, it's giving us the same value because it's actually that absolute value factor is really the distance between the center and any point in the endpoint of the interval that we're looking at. So, but still, we have to check both endpoints, and in some cases, well, since we're looking at the interval between 7 and 9, that is 1 unit to the right and 1 unit to the left. All right, so we just found the maximum value. Well, it's actually one single value that is going to be equal to 1. Let's find m. And m in this case, to find m, where is m? This value of m is found by computing the next derivative. That's why I took the third derivative in the original process, because that's the one that we're going to use to find the quantity m. So in this case, fn plus 1 of x less than or equal, or I think it's just less than, big M. And well, in this case, this is going to be the third derivative, or triple prime, less than m. And in this case, well, we are going to have that m in this case, which is the third derivative. So let's go back to what we got for the third derivative. For the third derivative, we got 10 over 27 x to the, or rather 10 over 27 x to the 8 thirds. So 10 over 27 x to the 8 thirds. Now from here, for this value of m, we need to check which one, x equals to 7 or x equals to 9. Which of these two evaluations is going to give us the largest of the two? So think about it. I'll let you think about this one. Which of these two evaluations will give us the largest of them? At 7, all right? Well, and that's because, well, we are plugging in a smaller value than 9 in the denominator. Getting a smaller number in the denominator means big value, as opposed to evaluating at 9. That's going to be a larger number, and no, that's going to give us a smaller number, and therefore that's not the maximum value. Well, so we need to compute then 10 over 27 times 8 to the 8 thirds. And in this case, well, this one, just skip it, because not the largest. Okay? Yes, I don't know why I did this. It's supposed to be a 7. Thank you. 7. All right. we may go back to Taylor's inequality here to find that remainder. Well, so number one, that's the remainder of using the second degree polynomial will be less than or equal that crazy number, this madness here, 10 over 27, 7 to the 8th thirds, and times the one that we got for the green quantity, and then that divided by 3 factorial. And well, let's just rewrite this in a nicer way. 3 factorial, which is 6, fraction inside a fraction, that's a complex fraction, and that's well less than or equal to 1 times 10, that's just a 10, over 27 times 7 to the 8th thirds times 3 factorial, which is 6. And guys, here is where I differ with the book. In fact, this is the same example as in the textbook. And well, if you read the textbook, it's kind of hard to understand what the hell are they doing there, because they just go, oh, and yes, that equals to that number, but where do they get that number? The book doesn't explain anything about that we have to find the maximum value, and it doesn't actually go back to let you interpret those inequalities as well, in one situation having a max and in the other situation having a min. If you read through the book, the way they go about it is just weird. So in this case, and also another thing, the most important thing I disagree with, the author of the textbook actually simplified this to decimals. That is, it simplified too early in the calculation, and we call that a rule of thumb is to not round until the very end. You know, especially when you're working in chemistry or in physics, significant figures and all that, well, carry all the roundings until the very end, or rather keep the exact values and just round until the end. So after simplifying this, this is going to give us 0.0034. Okay. All this crunching of numbers and symbols and derivatives and the like to get that value, but what does that value represent ultimately? Well, this value means that this is the maximum difference between the actual value and the approximate value when we use the second degree polynomial. Or if it's easier for you to understand this value, this means 0.34%. All right? So that's how off the approximate value is from the actual value. So they're off by 0.34%. Where, okay, let me go back to the picture. So at the edges of the interval that we want, that means these two quantities at the end, I know they look bigger, but it's actually the same value because of how bad the picture is. This means T2 and f of x differ by 0.34%. All right, that's in the outer end of the inequality. However, that's what we want to find, the largest value, the maximum difference. Of course, if we get closer to the center value, this percentage diminishes, and because it's getting closer to the actual value. All right. Now the question is, okay, let's expand a little bit without doing any calculations, without doing the whole problem a second time. What if instead we're not looking at the interval 7 to 9, but instead we look at the interval 5 to 11, for example? What would you expect this value of r sub 2 be? Would it be a larger value or would it be a smaller value? larger value because see how the approximation it's actually diverging from the original function. You know, it's getting away, or the actual versus approximate is getting larger at this point, at these endpoints. So there's a couple of things that we can do to improve the error, or to improve the to improve the maximum error. What would you do to reduce this gap? Add more terms, right? Add more terms, or narrow the interval. And guys, this is the type of thing that you're going to do in numerical methods and actually applications in the industry. You know, when you're working in a manufacturing of, you know, parts for cars or airplanes, you know, they have to have some specifications that so they fit in the actual manufacturing and they are not too far off, you know, because yes, I mean, in the manufacturing not every part is perfect. There's always some, you know, small error, and well, in situations you don't want to get these errors. Actually, you need even more refined accuracies, and well, you guys as engineers have the tools and the mathematics to get these improvements. Of course, I mean, think about how to make this better, like adding maybe 20 more terms, or getting the 100-degree Taylor polynomial. But I mean, do you have time to compute 100 derivatives and evaluate them? Not really. So that's why you are going to work on this using MATLAB, using some programming language, you know, so you can just input the data and get this done for you. But I mean, what all this that we're doing here is the behind the scenes of getting these improvements.